Let's put all the information together that we've learned about end behavior and interior behavior and graph a polynomial function. When you approach the graph of a polynomial function, here's the procedure that you want to think about. Number one, identify the leading power function and determine the left and right end behavior of the graph. Then, number two, solve p of x equal to 0 to find the zeros of the function and plot them as x-intercepts. Don't forget to consider the multiplicity of each 0 to determine if the graph bounces or crosses at each x-intercept. Number four, find the y-intercept of the graph by evaluating p of 0. That's equivalent simply to plugging 0 in for x. And then number five, carefully sketch the graph of the polynomial function and we'll approximate the turning points with the calculator. We can predict how many turning points there are, but we will approximate their location with the calculator. So let's apply this procedure on example 6. Graph the following polynomial functions. Now we don't want to sketch the graph, we want to carefully construct the graph. So here we have the polynomial function f of x. Notice it's already in factored form. That'll be helpful when we get to locating the x-intercepts, but as far as finding the leading power function, makes us think a little bit harder on this step. So the leading power function, remember, is the highest powered term of a multiplied out polynomial. I don't want to have to multiply everything out, so I'm just going to anticipate what would my highest powered term look like if I were to multiply it out. So right here, I have my first factor, negative 1/2 x. That's degree 1, and I'm going to include that coefficient with that term. If we were to FOIL this out, our highest powered term would be x squared. Yes, there would be other terms, but they're going to be of lower degree. And this one, our highest powered term, is x. So if I multiply straight across those factors, we're going to discover what our leading power function would be. In this case, it would be 1/2 x to the 4th. Notice that is even degree. As we learned previously, even degree has the same end behavior. So this end behavior is going to resemble the smallest even power function that we can think of, which is x squared. So remember, x squared is a parabola where both ends open up, and negative x squared is a parabola where both ends open down. So our even degree x to the 4th power function is going to be similar to our even degree power function x squared. Because we have a negative leading coefficient, it's going to follow the behavior of this one. So we can say both ends fall. So let's just make a note of that on our graph. The left side is going to fall and the right side is going to fall. Next, we want to determine our intercept. Remember, intercepts come from the zeros of the polynomial function. So we not only want to recognize the 0, but also the multiplicity of the 0 and the behavior of the graph at that 0. So I'm going to make a little table to keep all this information organized. Because our polynomial here is in factored form, the zeros will be pretty easy to determine. If we look at our first factor here and set that equal to 0 and solve for x, we would get x equals 0. The exponent on that factor is 1, so this 0 has multiplicity 1. And remember, at odd multiplicity, the graph is going to cross the x-axis. Our second factor here has a 0 of 2. Because the exponent there is 2, the multiplicity of that 0 is 2, and at a 0 of even multiplicity, the graph is going to bounce. And our final 0 comes from this factor. It has a value of negative 2. The exponent on that factor is 1, an odd number, and odd goes with cross. So let's put this information on our graph. We have a 0 at x equals 0. The official ordered pair there would be 0, 0. And I'm just going to put a little c there to remind myself that the graph is going to cross the x-axis at that intercept. The next 0 is at x equals 2. This would be the official ordered pair 2, 0. And our graph is going to bounce at that x-intercept. And the last one we have there, 0, negative 2, that's ordered pair negative 2, 0, and our graph is going to cross at that x-intercept as well. Now, if you look at this point, 0, 0, it doubles as the x and the y-intercept. So I don't need to do any more work to find the x-intercept. So at this point, I can begin to sketch the graph. We know the left end has to fall. It's going to cross at this x-intercept. Somewhere it has to turn around, I don't know where, but it's going to have to turn around and come back through and cross at this x-intercept. Then it's going to have to turn around somewhere, I don't know where, and head to this x-intercept, bounce, and then fall from there. So I'm sketching this in because I don't know the exact location of these turning points. We'll approximate those with the calculator. So in the calculator, we'll go to y equals, and we'll type in our original function. I'm just going to write it as negative 1/2 times x with the division bar there. X minus 2 squared times x plus 2. And we'll take a peek at the graph. So it looks like we have the right behavior. Now we can approximate those turning points. So this one is very close to x equals negative 1. 1, 2, 3, 4. It's about negative 1, 5. This one stretches down to about y equals negative 2. So with that additional information, we can make this one a little taller, this one a little lower, and then we'll have a pretty accurate sketch of our graph. Remember, polynomials are smooth and continuous. Okay, not bad. Now that polynomial was in factored form. Our next example is not in factored form. This means it's going to be easier to identify that leading power function, but we'll have to work a little harder to get it factored in order to find zeros. So our leading power function is x cubed. This is an odd degree leading power function, which means we're going to have opposite end behavior. And remember, we can relate all of our odd power functions down to our basic x cubed function. And we can see here with the positive leading coefficient, the left side is going to fall and the right side is going to rise. So I'm going to put that on my graph. The left side is going to fall and the right side is going to rise. The next thing that we want to work on are intercepts. So let's find the x-intercepts. X-intercepts are always obtained by setting your y-coordinate or replacing your function with 0. Now I've got a 4-term polynomial function. Remember, one of the techniques that we learned for factoring a 4-term polynomial function was grouping. So we can apply that on this example. So between our first 2 terms, we have a greatest common factor of x squared. If we take that out, that leaves behind x plus 2. I've got a plus in between the pairs of terms up there, and I can already see, even though those don't have a greatest common factor, that matches the binomial that we got from our first term right here. So now comparing these 2 terms, the first one here and the second one here, they have a greatest common factor of x plus 2. So we can take that out, and that's going to leave behind x squared plus, if you take the x plus 2 out of that second term, you get x squared plus 1. So we have it fully factored. Now we can set each factor equal to 0 and solve for x. The 0 that comes out of this factor is x equals negative 2. Now the zeros that come out of this factor, if I set it equal to 0, and solve for x. Notice when we take the square root of both sides there, we're going to get plus and minus I. Don't forget, imaginary zeros don't correspond to x-intercepts. So it looks like we're just going to have one x-intercept on this graph, and that's the ordered pair negative 2, 0. Now, even though this is a degree 3 polynomial and we would anticipate at most 3 x-intercepts, the key phrase there is at most. It can have 3 or less x-intercepts. So we have ordered pair negative 2, 0. This came from a factor with an exponent of 1. with odd multiplicity, we can expect our polynomial to cross the x-axis there. Let's also find the y-intercept of this graph. Remember, to find the y-intercept, we set x to 0. So replacing all of our x's with zeros, looks like our y-intercept is equal to 2. So as an ordered pair, we can call that 0, 2. So let's plot that on our graph. Ordered pair 0, 2. Now let's see if we can sketch the graph from the clues that we have here. We know the left side is going to fall. So once it passes that leftmost x-intercept, it's not going to change its behavior. It's going to fall forever. And then we know it has to pass through 0, 2, but it's never going to turn around and come back through the x-axis again. There's no x-intercept. So it's just going to rise from there. Now, to be sure we have it right, and maybe to refine the shape of our graph, we can come back over here to our calculator and take a peek at this graph. So let's type in our original function. And we did a pretty good job. We can see that it's leveling out right about x equals -1. It comes up, it levels out, and then it passes through. So making our graph a little more particular. It's going to come out, level out about here, and then rise indefinitely. So that one's interesting. We had a lot of terms, but the polynomial graph itself was even simpler than the previous example. Okay, let's go through this procedure on our last example. So first observe we have a degree 4 polynomial function. Our leading power function is x to the 4th power. With an even leading power function, we anticipate the same end behavior. Now remember, for our even powers, they're either going to resemble x squared or negative x squared. This one has a positive leading coefficient, so it's going to have the same behavior as positive x squared. So both sides are going to rise. So we'll make a note of that. Left side is going to rise, and right side is going to rise. Then we want to determine our x-intercepts. Now, if we look at this polynomial, it has 5 terms. So the previous method of factoring by grouping will not apply on a 5-term polynomial. So we've seen this before. We studied it in chapter 2. How do you factor a polynomial with this many terms? Well, we find the factors one by one. We're going to find the p's and q's. We're going to apply the rational zeros theorem. So let's find the zeros of this polynomial. As a reminder, with the rational zeros theorem, we're going to form a list of possible zeros of the form p over q, where p is a factor of our constant term, and q is a factor of our leading coefficient. Now, this is that easier case scenario where our leading coefficient is 1. So we'll take all the factors of 4, put them over 1, which really just leaves us with all the factors of 4. So possible rational zeros would include positive and negative 1, 2, and 4. So we just want to pick a number from that list and verify with synthetic division if it's in fact a 0. So I'm just going to start with the first number in that list, which is 1. And remember, we pick up the coefficients of our polynomial. So we have 1x to the 4th, negative 1x cubed, negative 4x squared, 2x, and our constant term is 4. So we just pick out the coefficients. We bring this first number down, and then we multiply and add all the way across. So we multiply the number in the box times the number on the baseline, and then we add vertically to get the number on the baseline. So what we're interested here is that last spot. We're looking for a remainder of 0. Since our remainder is not 0, we know that 1 is not a 0 of the polynomial. So this graph will not cross the x-axis at 1. Okay, let's move on to the next possible 0 in the list, which is negative 1. So I'll take negative 1, I'm going to use the same grouping of coefficients. And we'll run our synthetic division process. And lo and behold, we got what we were looking for. Since this has a remainder of 0, we know that -1 is, in fact, one of the zeros. Now remember, with synthetic division, that first line represents a degree 4 polynomial. So this last line of coefficients represents a degree 3 polynomial. So we can actually continue our synthetic division process. If I ignore this spot right here as the remainder, we can just continue our synthetic division process on this degree 3 polynomial, because the remaining factors are going to be factors of this depressed polynomial. So I'm just going to try the next number in the list, which is 2, and attempt to reduce the polynomial a little bit further. So we bring down our first term, multiply the number in the box times the number on the baseline, and then add vertically. And just repeat that process. Awesome. We came up with another remainder of 0. So we know -1 is a 0, we know -2 is a 0. Now we're dealing with a degree 2 polynomial. So up to this point, if we want to keep up with our function, one of the factors, remember, if the 0 is -1, it came from the factor x plus 1. If the 0 is 2, it came from the factor x minus 2. And then my other factor is right here. It's degree 2. So we have 1x squared plus 0x minus 2. I decided to convert that back into algebra there because now we're dealing with a degree 2. Now, that's not exactly the difference of 2 squares, but we can kind of force it to be the difference of 2 squares by factoring it as x plus the square root of 2 times x minus the square root of 2. If you don't like factoring it like that, you can also set this equal to 0 and solve for x using the square root method. But now we can read both our zeros and our x-intercepts. So from our first factor, we have the 0, -1. And if I put that as an ordered pair, there's my first x-intercept. The zeros from the second factor is 2. And as an ordered pair, our x-intercept would be 2, 0. Coming out of our third factor, the 0 there is negative square root of 2. And negative square root of 2 is about 1.4, so we'll know where to put it on the graph. And then finally, square root of 2, 0, which we can think about as 1.40. Okay, let's update our graph. So we have ordered pair -1, 0, -1.4, those are going to be kind of close together, negative square root of 2 and 0. We have 1, 0, nope, I'm sorry. That's supposed to be 2, 0. And 1.40. Square root of 2 and 0. Now, the polynomial is going to cross at all 4 of those x-intercepts. All of those zeros had a multiplicity of 1. And by the way, we also need our y-intercept. There's a great shortcut that you can use for a y-intercept. To illustrate this, let's look back at this last example. The y-intercept that we got for the last example was 2, and notice that's what we had right there. So when we replace all the x's with zeros, the only thing that remains there is the constant term. So on this example, if we replace all the x's with zeros, again, we're just going to be left with the constant term. So our y-intercept here is 0 and 4. So based on the information that we have, we know it's going to rise, it's going to cross, it has to turn around somewhere. It's eventually got to pick this up. So it looks like we're going to have basically a W shape. But we want to know, where are those turning points going to be? How low do we need to go on the graph? So let's take a quick peek at our calculator. We'll type in our really long function, x to the 4th. double check and make sure I did it right here. Missing a cube. I knew something felt wrong. X cubed minus 4x squared. Okay, that looks good. All right, we have a W shape. And notice our turning points, they're not quite symmetric. This one's a little bit lower, but they're really, really close to the same. And our maximum is not at the x-intercept, it's just to the right of the x-intercept. So refining our graph, we have this. This one's going to go a little bit lower, and we have a pretty accurate graph. So there's a lot of things to think about when you graph a polynomial function. Each skill on its own is pretty straightforward, but when you put it together in a problem like this, you can maybe stop and appreciate all the skills that you've acquired up to this point.